This is the recording for the Waves lecture. This is week 10 of Oceanography. Remember, there are two Waves lectures. First one is in the Content tab. That is the full Waves lecture. That includes all the embedded notes and essentially the comprehensive lecture. Instead, I'm going to be lecturing from the second lecture. While I share my screen right now, you'll be able to see what that is. This is the Mini Waves lecture. The Mini Waves lecture, of course, is found under the folder for this week, under the week 10 folder, and it's titled Mini Waves Lecture. Now remember, all the stuff from this lecture is found in the larger lecture. It just has less of the content or note slides and a little bit less of the pictorial slides. You're going to notice, though, more so than in typical lectures, there are a lot of content slides that I've maintained in this one as well, because there is a lot of very specific text. And so as we move along, I'll stop and pause on what I'm calling the text slides. Okay, so we're diving into waves. This is one of the worst definitions, I think, of all of oceanography. If we were playing Jeopardy and Alex Trebek put this up there, I probably wouldn't even get it right myself. So by definition, a wave is, quote, a disturbance caused by the movement of energy from a source through some medium. Again, what? Right? But if you break it down and you make it in more layman's terms, it actually does make sense. Okay, so the first thing that we know, of course, is a medium is some mobility, right? It has to be in something. Water, for example, is the one that we're talking about in this class, but it's also the material that we're most familiar with that a wave would move through. And water, of course, can exist in a solid, a liquid, or a gas. And waves and any other type of movements can occur in multiple mediums, right? Meaning not just in a liquid. So that's the ending portion of the definition. The second portion begins with the start of it all. Disturbance caused by the movement of energy. So that's you doing a cannonball in the water. That's you throwing a brick or a stone or a pebble in the water. That's you putting your hand on top of the water and stirring it. It's any change in flatness, right? And then what will happen is, generated from the center of your hand or the center of that rock or the center of your cannonball or from the sides, depending on in which direction you push it, the movement will go through the medium in a shape, okay? What's essentially happening is energy is moving through a medium in a particular shape. And we call that shape, the transfer of that energy through the movement, that shape is the wave. Okay, so the movement itself is what we classify as the wave. Of course, there are many different sizes and shapes of waves. The obvious ones that you guys are familiar with, of course, are the swells, regular inundations, right? They're horizontally marching one right after the other. I call them the marching rockets, equally spaced apart perfectly as they do their kicks. And you'll notice that the one in the front reaches a peak higher than the one in the back, and that's again because it's approaching the shallowness of the water. And as it gets shallower, the energy from the bottom changes how the shape of the wave rises up. Okay, so that's one type of wave, a swell. A second type of wave is a breaker. A breaker, of course, implies that the wave itself has broken. Okay, so if a wave looks like this, but this wave looks like this, it has literally broken its peak. So that's a wave break or an ocean breaker. This happens anytime where the energy of the water as it's traveling through is higher than the depth of the water. So as the energy is moving from offshore toward nearshore, for example, as a tide is pulling in or as wind is blowing, it's going to push the water and the energy in the water so high that the depth is less than that energy. So it has no choice but to rise the water up, making it appear, of course, that the water has gotten higher as it approaches shore. Really what's happening is the depth of the water is shallower underneath it, so the water is just rising up. Third type that's demonstrated here is what we call chaos. A chaotic wave, of course, is sort of a choppy, unpredictable nature. It typically happens when a tide or the regular movement of the water is in opposition to the wind, or there's more than one wind or storm type coming in opposite directions. And so you can't have regular patterns. So we call those chaotic waves. This is typical, right? The typical picture. And I want to just use this one more time. We saw this on the slide before to point out that waves approach the shore in a parallel pattern. And then they start to bend toward the shore and they get higher as they approach the shore, but they're still equally spaced out until, of course, they start to pile up and the energy starts to pile up and the one on the front rises up and eventually this one becomes the broken wave. This figure is one of the key figures that I want you to spend a lot of time working with this week. When you go through the virtual waves lab, which is lab number 7 that you're going to be completing this week, you're going to be using a plunger. Think of it like a big giant plunger in a toilet bowl, right? And you're essentially going to be using larger and smaller plungers, so bigger and smaller items, and you're going to edit the frequency, the speed to which that plunger goes in the water. So if I had a small plunger, I would make little tiny waves. If I had a large plunger, think that it has more energy, right, driven through the water, you would make taller waves. If I were to take that plunger and go quickly, I would make many waves. If I were to just make that plunger go every couple of seconds, for example, I would make waves more spaced out. So that's how wave dynamics work. And you'll play with the plunger, of course, in your virtual waves lab. You'll then be pausing and reading the frequencies, the speeds, measuring the heights and the wavelengths. And so this figure is going to help you to understand exactly what it is that you're looking at. Okay, so there's going to be, I believe, 7 different definitions or explanations toward waves, 6 of which actually, are demonstrated here on this figure. And then as we move forward, we'll sort of collect more as we go. Okay, so the most important thing to notice with a wave is that a complete wave goes trough to crest to trough, meaning I've completed one complete up and down. Okay, we could equally go from crest down the trough to the upper crest. Doesn't matter if you go low, high, low, or high, low, high, okay, as long as you complete one complete length of a wave. So the very first term here that we're going to notice is something called a wavelength. A wavelength is from the crest of one wave to the crest of the next corresponding wave. Imagine this is person number 1 standing in a line. There's person number 2 standing in the line, and the space between them is the length. Okay. The next component that's important in a wave is the height. Okay, so the height, of course, is from the top of the wave or the crest to the bottom of the wave. Remember, the bottom of the wave is called the trough. So from crest to trough is the definition for a wave height. From the top of your head to the bottom of your feet, that is your height. Same thing applies with a wave. We just call the top of the head the crest and the bottom of the wave the trough. Excuse me. Next key term here is going to be the term orbit, and you can see it here represented by this circle. Okay, so the orbit looks like that. An orbit is the circular path that the energy travels as it progresses through the wave. In other words, water doesn't necessarily, or the energy in the water doesn't necessarily move through it in a straight line, right? The path doesn't occur in a straight line. Instead, you have high points and low points, high points and low points. So what's actually happening is you're completing a full circle. What goes up must come down, so the equal sides match up. So this is the path that the individual water molecules are going to essentially travel through at the water's surface. Okay, so you're going to see this come up in another couple of slides with a bird on a figure. Another key term that you're going to notice here is frequency. Frequency is the number of waves passing point A or B for each second. Now it can be A or B, or for that matter, C, D, E, F, G, right? Doesn't matter. You just pick a fixed point. Let's say we pick A as our fixed point. Then we would stare at A, and as our wave train begins, as the water starts to move in this direction, every time we hit a crest at A, we would count. And we would do that, for example, for 30 seconds. So You would then take your number that went by per second, and that would give you the frequency. Next term, the period. This is the time required to travel from A to B. So how long essentially does it take to go across that wavelength, to go from crest to trough to crest? You just literally can measure that distance by taking the wavelength and figuring out the time it takes to travel from the top of one wave crest to that same corresponding wave crest at its next peak or cresting point. Okay, so we covered a bunch of terms on this figure. We covered crest, trough, we did wavelength, wave height, orbit, frequency, and period. Okay, the next couple of slides, I give you a little bit more specifics and definitions on orbits. And hopefully this is that bird I was talking about. Hopefully this will help you to understand what it means by the energy movement or travel through the surface of the water. Okay, notice that the bird never goes under the water. On the surface, on the surface, on the surface. Okay, it doesn't literally go under and then pop back up again, ever. But where does the energy go? Notice it started underneath, pushes up, that would make our crest, loops around, now the bird is riding the crest, right? Loops around, constantly riding until the bird has essentially traveled down the trough, up the crest, and back again, right? So it started on the top of this side, traveled down, it's traveling down, and eventually back up and over so that it ends up back at the bottom. The entire thing traveled is the energy that's moving it forward. That is called the orbit. Of course, there's not only one molecule of water in the ocean, or anywhere for that matter, right? And of course, there isn't just one wave. So there isn't just one bit of energy moving, which means the orbits are synonymously or simultaneously moving through the water if the depth is the same at the same pace. You'll notice at the top here that the top of the orbit matches the crest and the bottom of the orbit matches the trough. That explains, of course, that as you go across, you're going from crest to trough each time as the energy travels through the water, okay? But we know, of course, that energy also transfers downward. How far downward it travels is a question, literally, for the explanation behind the energy needed or the effort needed to push that energy down. So that seems a little bit complicated, right? So I like to use the example of a basketball. If you were to hold a basketball in your hand and then hold it on both sides, hold it over your head, and slam that basketball to the ground as hard as you possibly can. No matter how much energy you have, you're going to slam that basketball. It's going to hit the bottom and it'll bounce back up. But I don't care how much energy you have, you're never going to bounce it, let's say, for example, to the ceiling. Okay? In other words, there's a certain distance to which the energy in your arms and the push down that you have, that the ball and its rebound can have going up. Stronger people, taller people are going to change how high and low it can go. The point being, it's the energy that you put forth to drive it upward. Okay, with all your effort and might, you'll get it higher, but not forever. Okay, that can't happen. Change your thought process now, okay, and take that same basketball, hold it over your head on both sides, and just simply drop it from above. Don't use any energy whatsoever. The energy that it falls down with still has energy, but when it hits the bottom, will it bounce as high as the original method? No. So the amount of energy that causes the wave to move through the water literally determines how far down the energy will travel in the ocean column, similar to how high the basketball would be going upward with the energy or the force you use to push it down. So if you have a lot of energy, okay, a massive storm, then of course the water raises higher, and if it raises higher, that's like you really using all your effort, it can get pushed down even lower, okay? Conversely, if you just have energy, it's certainly not going to go as deep. So there's always going to be a set point, okay, a depth of water to which, notice that the orbits are not here, to which the energy cannot pass it. We call this deep water. Now, of course, what does deep water mean? Well, it's actually going to have a set depth depending on the energy source to which it travels. So if the orbit, remember that's what these circles are called, does not reach the bottom, we say that we are in deep water, or we call it a deep water wave. In that particular case, what we've actually predetermined mathematically is that 1/2 of the wavelength of that wave, remember a wavelength is from crest to crest, 1/2 of that number cannot reach the bottom. So that's what this is telling you. So let's do some math here, okay? Let's say we start at the 0 mark and we end at the 10, let's say meter mark. Half of that number would be 5, okay? If the depth of the ocean is 1, 2, 3, 4, 5, 6, then of course this only makes it to here. The energy cannot reach deeper. So it's essentially like saying that you're dropping the energy through the water until the energy has no more energy to go. And so it's not hitting the bottom. If it doesn't hit the bottom, it can't ricochet off the bottom to push itself back up again. So there's no new energy. That's in a deep water situation. Of course, in a shallow water situation, the opposite would happen, right? If we know that half the wavelength is 5, if the depth of this water were 4.9999 or less, it would hit the bottom, and then we would end up having a shallow water scenario. Okay, so I gave you a whole bunch of different specifics for waves. Remember, we did crest, trough, wavelength, height, orbit, frequency, and period. Here are 3 more components that we need to cover, starting first with fetch. Fetch is the uninterrupted distance over which the wind blows without significant change in direction. It should go without being said, but perhaps I should say it for you. When we did the atmospheric circulation lecture and then the ocean circulation lecture, we were giving a 1-2 punch to say that the wind moves the surface layer of the water, right? Surface circulation, the currents in the gyres are moved by what? Wind, right? We called it wind-driven horizontal surface circulation. So of course, the wind is what's moving the water, and the energy type pushes it in a distance through a medium, and we call it a wave. The fetch literally means it can go uninterrupted across the surface layer of the ocean, never hitting anything. So you're in a deep water scenario, so it's not ricocheting off the bottom, and the length of the fetch will be the direction to which it's pushed until it gets interrupted, right? Because this is uninterrupted, and there can be no significant change in direction. So it's in the path of a straight line. Let's say, for example, that you had an island right in the middle of the water. Then clearly you have now interrupted the fetch, and that can change the distance to which the water can travel. The other component I want you to notice in this figure, and I always call this reading the water. If you watch a wave tank, or you literally stand on a pier and you read the water, and you see that it looks like little scales, and they're all bending in the same direction, that's fetch, right? That means the wind is pushing it from behind. Again, all moving. It could be just the same as making them arrows, right? Little fish scales, little mermaid scales. It's telling us that everything is moving uninterrupted from the left of your screen to the right of your screen. Another way to remind yourself of this or remember this is if someone came up behind you and they pushed you from behind, which way are you going to go? You're going to fall forward, right? You're going to be going in the direction to which you got pushed. The wind is what's doing the pushing. You don't fall backwards on them. So the fetch is pushing you in the direction to which the wind is pushing you uninterrupted. Next term is wave break, which again we covered before when we talked about the 3 different types of waves. But this wave break is a little more specific because what it does is it shows us, remember we talked about deep water waves versus shallow water waves? It shows us actually that the depth of the water makes a dramatic difference as to when the break or wave break will occur. Okay. You've all heard this term surf zone, right? That's the area where essentially as you're walking into the water, you feel like your feet are being pulled out from under you. Or if you're trying to get out of the water, it's the hardest part, right? Part you kind of struggle because again, your feet are being played with. Next thing you want to look on this figure is going to be your marching bands, okay? Notice what happens. You start to see white caps as you get closer to shore. Notice what's happening. Shallow, deeper, deepest. So in deep water, you have regular, straight fetch. In shallow water, you start to get a break, and that occurs in the surf zone. What it means is you've gone from a deep water wave to a shallow water wave. Where do the waves break? Based on depth. They break in a shallow water zone. Next term is refraction. Hopefully you remember the refractometer. That's what we used in the lab 5 to look at the salinity of water. It meant to bend the light based on the salinity measurements, and then it was able to tell you how much salt was in the water. Well, here we're going to bend the energy as it travels through the wave, travels through the medium, right? The wave in the water. So when waves do not approach parallel to shore, the wave line will bend to become parallel to shore. In other words, those marching soldiers are always going to try to come straight toward home. So when they're not parallel, here they look perpendicular, look what happens. They start to become parallel. That's because of the bending or the refraction. Another example showing you the same thing. Refraction, bending. So the crazy definition for waves, right? The movement of energy through a medium from a disturbance. Really what's happening is that orbit, that circular path that travels from crest to trough to crest, is energy that is gained and lost over and over again, okay? So as that happens and it's gained and lost over and over again, what you're technically having happen is that you're getting a small net movement of water in the direction of the wave. In other words, whichever way the wind is pushing it. The person who discovered this concept is called Stokes, so it named it after himself, Stokes drift. We like to call it mass transport. Okay, think of it like public transportation. It's the massive total movement in the direction to which the subway car takes all the people. But unlike a subway car, which travels a straight line, right? Waves do not. So the net amount of movement, fastest way to get from A to B is a straight line. Well, we didn't travel a straight line. So the net movement, of course, is less. Here is your mass transport. This is you on the subway car. If you were to go to the next stop, you would go in a straight line to the next stop. But because you have to travel the orbit, you can't just go straight. You have to come all the way down and around. You have to complete a complete orbit. That means that you went backwards as you went down and forwards as you went up for a total mass transport of only that net amount. It's not the diameter of the actual orbit itself. So mass transport is showing you that because you gain and lose energy, the total amount moved forward is a net positive, but it's not the total net positive if you were to travel in a straight line. In other words, this is not the smartest path to travel. It takes too much work. But in waves, that is how it works because of the actual shape, right? The movement. So now we've gone through all the components of a wave. You'll then complete Lab 7, where you'll be essentially working through plungers and messing with amplitudes and frequencies to manipulate higher and lower waves. Okay, so essentially what's going to happen is if you have big energy, big plunger, okay, let's just say that this is our surface. If you have a big energy and a big plunger, then you're going to be able to go really deep, really deep, really deep, because the energy is pushing it down. If you use a tiny plunger, maybe not so deep. Okay. Similarly, clear this out again for us. Similarly, if we were to go fast, right, we make our plunger go every half second, for example, or if we go slow every 2 seconds, for example, what do we do to the wavelengths? Skinny wavelength or small wavelength? Longer wavelength. So we change the height of the wave and the wavelength itself simply by manipulating those two things. How much energy we use and how often, or the frequency, how often we move the waves. So when we classify our waves, those become really important, okay? We have two different types of forces in the classification of waves. That which causes the wave, that's the energy itself, and that which stops or restores the energy. Okay, so the dominant force trying to return the surface to flat. In other words, constantly trying to flatline. But there's always going to be a disturbing force. What's the main disturbing force? Wind. And if the wind is blowing, the water is moving in the direction to which it gets pushed. So those are our two wave classifications. In other words, something starts the wave, that's the energy that starts it. That would be you doing a cannonball in the water, throwing a rock in the water, pushing your hand through the water, right? Just as much as the wind can be. And the restoring force is always trying to get it to flat. Okay, so here's a list of different examples of disturbing forces, which of course the wind is the most predominant one, but there are some other examples. Here's our plate tectonics example. And here's our classic gravitational pull based on the Coriolis. Restoring force example is the gravitational pull trying to restore us to flat, and the ability for water to have cohesion so it has surface tension. This then gives us a whole bunch of different types of waves. Now we talked about shapes of waves, chaotic waves, swell waves, progressive waves, right? Wave breaks. But really, we can have different types of waves that are generated. So, of course, if the disturbing force is wind, the type of wave that we have is a wind-driven wave. That's your common, typical wave. Surface tension, of course, because of cohesion, you're going to get a ripple or a capillary wave. In a gravitational example, you either have a Secchi or a tidal wave. Again, a tide, by the way, is a tidal wave, and tides are going to be the next lecture. And finally, if you have a plate tectonic event, everybody's running screaming because that is how you get your biggest, baddest, worst waves of all, or tsunami waves. Oops. Remember when we introduced the concept of deep versus shallow water waves? All we did was we took half the wavelength, right? We had used an example of 5. Okay, so we're going to use that particular example again. Okay, we're going to use 5 as our halfway point. If the wave cannot feel the bottom, it's going to be a deep water wave. That means the depth is greater than 5.01, right? Here's our orbit. We slam our ball as hard as we can. It can only go back up the same energy to which we pushed it down. It does not hit the bottom. Same amount of energy for each one. This is going to cause a greater distance to travel than the trough, but notice that the absolute amount reached is still not the bottom of the ocean. So that's a deep water wave. Remember, a deep water wave is a wave in which 1/2 of the wavelength is less than, okay, the water depth. Or the way it's written here is the water depth is greater than 1/2 the wavelength. Only wind waves can be deep water waves. Okay, so middle of the open ocean, those are wind driven. Now, of course, there can be other waves that occur in deep water. Doesn't mean that nothing else exists there, but wind driven waves are always a result in deep water. Shallow water, on the other hand, I'm going to make it a little bit easy for you, is just going to be the opposite. I'm not going to make you do any crazy math of 1/20th, okay? So now we're just going to say that you take that same waypoint, okay? That's half the wavelength. Sorry that I had a little feedback there. And what you're doing is you're going to compare it to the depth. And if the depth is less than this number, then it hits the bottom. And so you're going to have a shallow water wave. Here it is. Now, remember I said you could read the water, right? And we had originally said if you see water moving in this direction, we know what was pushing from the left to the right. Well, you can also read the surface of the water. In a deep water wave, you're going to have perfect orbits, perfect circles. So the water is going to always look rounded. Well, if it hits the bottom, it becomes a pancake, right? It smashes this in half. So look what happens. It flattens the top of the surface. So as you read the surface of the water, you're actually able to tell that the water is entering a shallow water zone. Even more importantly, once it reaches that shallow water zone and becomes too shallow, the next thing that you're going to have is your wave break. So this is our surf zone. Okay, so look, cannot hit the bottom, deep water. At this exact point, this is where it's going to be equal. We call that a transitional wave. So you go from deep to shallow by passing through the transition. That's an equal amount. In this case, our example, it would be exactly 5. Okay, this is where the water is greater than 5. And over here, this is where the water is less than 5 meters, for example. Now look, we can read the water. Rounded and perfectly orbital. Starts to get pointy. Why? Because it hit the bottom. Raises up a little, even pointier, and then all of a sudden there's nowhere for that energy to travel, so it breaks. Notice, by the way, I'm going to clear this out quick. Notice, by the way, that in this image, you also see an arrow that looks like it's going back and forth. This is representing disturbing force and restoring force. That's what's actually happening in the surf zone. So that's why you see an arrow with both angles, because the disturbing force is still wind driven, but the restoring force is trying to make the water flat. You're going to be asked a bunch of questions in the extra credit component, also when you're doing your mastering, and as you're reading through and completing all of Lab 7. And the main questions are always focusing on one specific topic. How does a wave break at shore? Well, we know it's wind-driven offshore, that a deep water wave must move through a transitional zone. It then feels the bottom, and as it moves forward and feels the bottom, it essentially trips on itself, going from an orbit to an elliptical. So from a circle to an elliptical, top of the wave looking like this versus like this. And ultimately, the crests are going to become peaked. The wave height has increased. It's more there than it is there. And the wave is going to slow down. Why? Because we have our restoring force and our disturbing force working in opposition as we approach the shallow water. Finally, the wave length will decrease. Right? Bigger wavelength, less wavelength. Here's an image showing you exactly that again. This is the one we saw before. So we have deep water here, shallow water here, orbit here, elliptical here, wave break here, restoring force and disturbing force here, trying to get us to calm or flat here. Big wavelength, smaller wavelength, less of a height, higher height. And that is what happens when a wave approaches shore. Here's another image showing you the same thing. I like to call these the Easter peeps, right? What this is telling me, of course, is that it's going in that direction. You can literally read the water. Why? The wind is coming from the left. The surf zone, of course, is that region where the breaking waves in the shore match up. So the wave becomes too high for its wavelength, falls over on itself, it topples over on itself. So exactly what happens when a wave breaks at the shore? Well, it stops, right? It stops being a wave. It stops having the energy movement because the restoring force is acting in opposition to the disturbing force, and there's nowhere for that water to travel. This is a good figure because it literally shows the energy amount. Again, doesn't hit the bottom, doesn't hit the bottom, just hits the bottom and doesn't have anywhere to go. Hits the bottom, really doesn't have anywhere to go. What's happening? These are going higher in height, they're peaking. Ultimately, it's going to break. What's happening here? The velocity will decrease. The energy of the wave slows down as it hits the shore. Why? It doesn't have anywhere to travel. The second lecture that we're going to cover with this material is tides. Okay, so now with these last two slides, we're going to connect how a wave and a tide are connected. Okay, so before I go over the two different types of interference, I want to remind you again where the tidal waves are located. So we're going to go back to the figure where we ID'd the tidal waves. Okay, it's a type of wave based on the gravitational disturbing force. Okay, so a tide is a regular periodic inundation of high and low as essentially we are orbiting and moving our water, and the disturbing force becomes the gravitational pull of the water around the entire planet. So what's essentially happening is that we're having two forces, okay, that are going to work in opposition to each other, similar to how constructive and destructive interference work in opposition to each other. Instead, though, we're going to call it, based on the restoring force and the disturbing force, the constructive and destructive, additive or subtractive cancellation of how the water is moving. So, two different types of interference. Number one, destructive, okay, bad. It cancels, okay? It's going to subtract the height or the energy to which you give it. It's going to take it away, okay? When a crest and another trough coincide. So if I were to go crest, or if I were to go crest trough, wave one and wave two, what happens? The amount that I gained here, I lost here. Destructive, no net positive, as opposed to constructive criticism, that which helps. This has an additive effect. Large crest, large crest. We have an up, we have an up, we have a net positive in height. Okay, so let's look first at constructive, which are represented on both sides here. Up, down of the green, match with up, down of the blue. What this gives us is a higher height, a higher crest. Make them not match up. My green is in opposition to my blue. This is going to flatten, giving me a lower total height. Again, constructive and destructive interference, which are going to also match up exactly with how tides come into play. Side view of this image, and this is the last figure for this PowerPoint. Okay, so remember, constructive gives us our highest heights. Destructive gives us our lowest heights. And if you have a mixed interference, sometimes you have highs and sometimes you have lows. You're going to notice that we actually have three different types of tides, one of which is called a mixed tide. And so this explains where that comes from. And that is the end of the waves lecture.